good moment, that good feeling, that good omen. I'm just going to weep.
Tubes per digit they wanted to represent. So they basically turned on or off those tubes to represent which of the 10 possible digits you could want. And it really didn't come to people until later than that, so that's 1948, that they really should just think about base 2 for everything. And the reason why bits are great is in the digital world, you can sort of take what's otherwise an analog signal and quantify it and just say, I'm going to say that one range of values, let's say it's a low voltage, I'm going to call that a 0. And a high range of values, I'm going to call it a 1. And if there's noise or imperfections in the circuit or anything going on, as long as that doesn't exceed these thresholds you've set up, then you'll get a nice clean signal out of it. And that's the main advantage of digital processing over analog processing. And so that's sort of at the core why everything we do, and especially for storing information, it turns out it's much easier to store one bit of information or a digital value than it is to store an analog value. And sorry, this kind of slides went a little crazy on animations. So the point is that we represent all the numbers in a computer as sets of bits, and I think you generally understand that fairly well. And so of course the familiar binary representation of integers, which we'll go over today, just uses a bit position for each power of 2. We can also represent values that are fractional, and we'll talk about that a week from today when we do floating point numbers, where what you do is to the right of the binary point, so this is no longer a decimal point, it's a binary point. And so something to the left of that would have weight 1, 2 to the 0. And the next one over would have weight 2 to the 1.
So how many are there? 27. Then each, so we'll have like, am I audible? Am I audible? Am I audible? Am I audible? Let me see if I'm okay. Oh, so am I audible? So am I audible? Yeah, I am audible.
But what you do is as you go to the right, that has weight 2 to the minus 1, 2 to the minus 2. In other words, this is 1, this is 2, this is 1/2, and this is 1/4. So we can represent, just like you do the decimal representation of fractions, we can do the binary representation of fractions. And that's the core of floating point number representations. And so it gets very annoying if you have, say, 32 or even 64-bit numbers to be writing these strings of 1s and 0s out. And so what we use...
Finish 2, 3, and 4 today. First of all, let us... So what is going on here? Like, what is it that I have to know? What is it that I am trying to... Okay, so I need the because it has no idea what my abstract is, right? Let's increase the brightness. There. Firstly, how many subsections are there based on the slide numbers and slide chapter? I'm not talking about the book though, but I'm not talking about the book though, right? I'm not talking about the book. I am talking about this. Forget about chapter 1 to 3. Forget about that. Forget about chapter 1 to 3. Forget. Forget. Explain whatever, explain the note based on the abstract. Like, explain the notes and use abstract as an example, one step at a time. Oh no, it's going to explain everything. Yeah. I don't know where did. Okay, this is cybersecurity. Uh, not guidance system. What was it explain? Okay. Okay. So they said that the most people think cybersecurity is just websites, malware, exploits, scanners, terminal. But underneath all cybersecurity is bits and memory. So this is the core idea of the nodes. So bits matter because in the nodes begin by saying computers only understand 0 and 1. This means an IP address like 192.168.1.1 is actually stored as the binary value for 192, binary value for 196, binary value for 1, binary value for 1. And a port state open is 1, close is 0. A vulnerability exists, 1, not found, 0. No, that's not the name, not Reconflow. It'll be a different name. So Reconflow, but then whatever. Reconflow is fundamentally processing binary cybersecurity states, not websites, not hacking, like just binary states. I would really appreciate if you could only use English for core explanation, not extra random English that overlaps the core explanation. Oh, okay. So bits. Computer has 0 and 1. So if you have open port, that's 1, closed port 0, subdomain found 1, subdomain not found 0. So everything will become in a binary state. So if you have a binary that's all 1, it's hard to read. In hexadecimal, it shortens it. So you have F and F. So 1, 2, 4, 8. So 1, 2, 3, 3, 4, 7, 7, 8, 15. So if you divide it into 4 and 4, so 15 and 15, 15 is F, 15 is F, right? Cybersecurity uses hexadecimal for packets, for memory, for shellcode, for hashes, for malware, for binaries. And so, for example, if I have 0x90, well, what is an NOP instruction? Oh, they will not explain it. Okay. Few things like NOP explanation, like NOP instruction, or all those words that I've never seen. Maybe it's best to explain them. What is NOP instruction? Again, asking means you're risking yourself, right? Okay, I still don't understand. Yeah, I still don't understand. So I'll get back to the lecture and we'll get back to you.
Uh, and what's become largely the most common is to group collections of 4 bits at a time into, and then represent that in base 16, or what's known as hexadecimal representation, using the letters A through F as values 10 through 15. And you'll spend a lot of time staring at hexadecimal numbers this year, and you'll get pretty good at being able to look at a hex number and just write it out in binary. The way I do it, just to tell you, is I've got the values from 0 to 9 wired down pretty well. And then I keep track of.
Will you be able to teach me whatever the transcript I copied? Let, if no, like, which is not surprising, that's fine. Then step one. Step one. What is it explaining? Only step one. Only step one. So computers only understand 0 and 1. So that's not the entirety of step one. Am I correct? What you explained is not the entirety of step one. Correct? Correct. So explain everything from here. Where is it? Here, based on what the professor explained or professor explained. Go. Very hard machine. It's not able to understand. That I know. But he also spoke about voltages and stuff. So actually, yeah, he missed quite a lot. So I'm just going to do, and I'm
Going
going to take a
on,
screenshot.
as long as that doesn't exceed these thresholds you've set up, then you'll get a nice clean signal out.
What is going on here? Explain. So scans 443. So open is 1, close 0. So internally port state will be binary state. Okay, so you said port state will be binary state. How can port state be binary state? Okay, you said that upper green region is 1 and lower green region is 0. Middle region is uncertain. The blue line is the real electrical signal traveling through the wire. So notice it wiggles, fluctuates, it's imperfect because real electronics are noisy. And so suppose intended signal is 1, voltage is not perfectly constant. Instead of 1 volt, you will have 0.97 volt, 1.03 volt, 0.95 volt. But the computer will still interpret as 1 because it remains inside the upper valid voltage. Same for 0. Instead of 0.1, you're going to have 0. All right, makes sense. Finally, I understood. If you actually understand what this guy, ChatGPT explains, you're a goat because he will not explain it easily. So, slide 1. Today is raining. It's really good. So everything is bit. So every single thing is bits. So computer converts everything into electrical binary bits. So one thing is that computer converts everything into electrical binary bits. And so each bit will be 0 and 1. So each bit 0, 1. So you can have open port, you can have close port, and also why is this? You can have open port, you can have close port. So what the computer does, the slice is the computer uses sets of bits to represent the instructions, represent numbers, strings, sets, data. So, so the computer uses sets of bits to represent data. To represent data, to represent information, instructions, strings. So instructions, informations, strings, sets, datas. So for example, if I have A is 65. Like that's for in ASCII code. So I'll have 1, 2, 4, 8, 16, 32, 64, 128. So that and the rest of them will be 0. And so in terms of what our example, if it scans, let's say scans one of the ports, if it's open, then it will be 1. And if it's closed, then it'll be 0. This doesn't mean the port state will be binary state. The port state is measured in binary state. But again, he'll not explain it properly. So in cybersecurity example, so if I have, let's say for example, the program will scan port 443 if it's open. So if open, then 1. If closed, then 0. Can you Yeah, keep this. Just going to save this because this will be important. This will be very important. Image one. So this will be image one, chapter 1.1. So based on the figure, what we have on the figure, the upper region is 1. So that, so if I draw the graph actually, I'm going to draw the graph. What's the time in Texas though? Oh shit, 2 hour 30 minutes. 6:31. Yeah, they're 2 hour 30 minutes away from us. So that's 1.1 to 0.9, and we have 0.2 to 0.0. If I draw a graph here, nope, I'm going to use a black color, a dark green color. That so this region here is 1, and this region here is 0. And this will also be 0. It'll wiggle. But binary is measured, so this, like usually, binary is measured in zeros and ones. However, like when measuring the voltage, you're not going to have exactly 0. You're not going to have exactly 1. So, but whenever you measure the voltage based on the graph, whenever you measure voltage based on the graph, you're not going to have 0 or 1 perfectly. Perfectly. It'll wiggle a little. Wiggle a little. Right. This is going to copy all those into Joplin, and this will be uh, lecture 1. That I know. So I am a human and I am allowed to watch Champions League, right? Well, then I don't have to argue. Like, I know Valentine says people who don't watch MMA is gay. Oh, I like this picture.
fractions, we can do the binary representation of fractions. And that's the core of floating point number representations. And so it gets very annoying if you have, say, 32 or even 64-bit numbers to be writing these strings of ones and zeros out. And so what we use, and what's become largely the most common, is to group collections of 4 bits at a time into, and then represent that in base 16, or what's known as hexadecimal representation, using the letters A through F as values 10 through 15. And you'll spend a lot of time staring at hexadecimal numbers this year, and you'll get pretty good at being able to look at a hex number and just write it out in binary. The way I do it, just to tell you, is...
So instead of base 10, you use base 1, base 2. So decimal is like 347, which is 3 times 10 to the square, plus 4 times 10 to the power 1, plus 7 times 10 to the power 0. Binary is that, yeah. The only difference is 10 to 2. Yeah, the base changes. So 152103. You have 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, so on, so on, so on, so on, so on, so on. Like, it can be represented entirely using bits. So each binary position has a power of 2 weight. So example, if I have 1110, then I have 1 times 2 cube, 1 times 2 square, 1 times 2 to the power 1, 1 times 2 to the power 0, which is 14. And then 1.20 is going to have 1 point, and what is it binary in 21, 2, 4, 8, 16, 16, 4. Wait. Why do you have 0, 0, 1, 1, 0, 1, 1, 0, 1, 1? Oh, is it? 20 by 100. Yeah, I know what it's 20 by 100. They'll not explain that, but 20 by 100 is what? 4 by 20 means 2 by 10, 1 by 5. So how is binary measured? How are binary values measured for decimal values? All right, so 1 by 1, 1 by 2, 1 by 4, 1 by 6, 1 by 1, 1 by 2, 1 by 4, 1 by 6, 1 by 8, 1 by 16, 1 by 32, 1 by 64, so on and so forth. So they're not going to explain that. So for second example, the 1.20, although I know how to do binary for 0.20, but make sure you explain that. Everyone wants to learn. Yeah, don't convert. Okay, but that's not how you do it. Yeah, he will make it much more confusing. He'll make it much more confusing. So he'll make it much more confusing. Anyways, um, so 1.20 is that the left of binary fractions, you have 2 to the power. So left you're gonna have 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. And so like I said, 1 by 1, 1 by 2, 1 by 4, 1 by 8, 1 by 16, 1 by 32, 1 by 64, and so on and so forth. 1.1 would be 1 by 1, 2 to the power 0 plus 1 2 to the power minus 1. So that's how you're going to explain it. So all you have to know is that left of binary is 1, 2, 4, 8, 16, 32. So the left of binary, left of binary and right of binary. You're going to have 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5, 2 to the power 6. Then you're going to have 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3, 2 to the power minus 4, 2 to the power minus 5, 2 to the power minus 6. Right? If I have 1.5213, then this you're going to have 5213 by 1000, which is 0.5213. So that is 0.5, 0.25. So this you can have 1 here. So 1.5213 you're going to have like that. So 1.5, 1.525, which won't work. 1.5125, and then you have to add, like, so you're gonna have no, that is wrong, because it's like saying you're gonna have 1.5. So this is 0.5, this is 0.25, this is 0.125, this is 0.0625, and so on and so forth. So what he's explaining is actually wrong. All right, it's wrong. But yeah, so left of binary is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4. Although I don't understand, like, how did you do the third example, which is very weird. I don't know how did you do third example when you literally just explained the left of binary is 2 to the power minus 1, then minus 2, minus 3, minus 4. Can you try adding 0.5 to 13? I don't think it's going to work. Oh, okay. Now it makes sense. It makes sense. So when you have 0.5213, right? So you're gonna have, let's see. So 001, so which means your first is 5 times 2 to the power minus 1 plus 2 to the power minus 2 plus 1 to the power minus 3 plus 3 to the power minus 4, and then so on and so on and so forth, right? So you're going to add them. So 1 point, you're going to add this, add this, add this, add this. Makes sense. Makes sense. All right. I understood. I understood. This is, so if I write um 0.5213, then this is 2 to the power minus 1, 2 to the power minus 2, 2 to the power minus 3, and 2 to the power minus 4. Right, makes sense. What I'm going to do is, because again, it's not able to. Because when you copy the, yeah, you can ask, okay, so why are you not copying the transcript? I did that. It's not able to understand anything. It literally doesn't understand. Like, it's going to make it more complicated because you haven't shown anything. It's going to make sure that you don't understand. Believe me, you'd rather save time on snipping the images and stuff. All right, explain slowly what's going on. Let's explain what is going on step by step. Um, I have uploaded images this time. I hope you can see. Also, one image. Let me understand, and then next image. Because again, it's not able to understand, right? I told you, so it didn't understand. So it goes all the way back to lecture one. 0x means hexadecimal number. And so 0x90, your binary value would be 1. Wait, wow, that'd be 90 though. Okay, so this is hexadecimal. Um, so they're not explaining. See, I told you they're not explaining. How did you do that? See, it's a very tough question. Very tough question. Very tough. But how did you get 144 from 0x90? Very tough question. Very tough question. I know the answer. I know the answer. All right. Um, so one byte is 8 bits, so it can have 8 binary positions. The smallest value is 0. The decimal value will be 0, and the hexadecimal value will be 0016. Right? So hexadecimal is measured in 16, base 16. Decimal is base 10, and binary is base 2. So they're not going to explain it, but make sure you remember it. So hexadecimal is base 16. Binary is base 2, and decimal is base 10. Holy shit. Does she even get that many views nowadays? Yeah, yeah, she does. She gets like 200,000 views, 500,000 views. She's really good. Exactly. Yeah, can you clearly explain what he supposedly betrayed and what truth you believe he exposed? Exactly. What did he do? Like, I don't think Sam betrayed anything. Like, dude has no idea what's going on. I like the comments because they're nice. All right.
The other class of operations we'll make use of a lot are shifting, which again is not something that you normally sort of as beginning programmers think about too much. And there's a curious feature that left shifts are always can track. Example is imagine we want to represent sets where the elements of the set are numbers ranging between 0 and 7. So 1 byte is enough to capture 8 cases. And we'll just, if we
Uh, so you said that maximum byte value is the binary is base 2, base 16. Okay, okay. Binary would be 2 to the power 0, 2 to the power 1, 2, 3, 4, 5, 6, 7. Yeah. And then you add them and output 255. Now total possibilities is from 0 less than or equal to x less than or equal to 255. So 256 possible values. Yeah. The professor introduces hexadecimal because binary becomes too long. If I have 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, I'm going to break them down. So this will be 15, 15. So that's in binary. There is also in binary. This is in decimal. This is in decimal. And F being hexadecimal. And this is hexadecimal. So for example, if I have FA1D37B, that's not decimal. What was 16 again? Hexadecimal. So C language will write 0x. So in C, if I have, yeah, C is the most important here. If, for example, if I have FA1D37B in hexadecimal in C programming language, you'll have 0xA1D37B. So this is indicating hexadecimal in C programming language. So how to convert um, decimal to decimal to hexadecimal. So if I have 0x90, and obviously this will be 90, this is represented in hexadecimal, and I have 9 times 16, 0 times 0 times 1, so that is 16, 9, 144, and 0, so that is 144. And 144 is the decimal here. And if I convert it to binary, so 1, 2, 4, 8, 16, 32, 64, 128, 128 and 16. All right. Um, from 1225. Um, I'm kind of running out of time when it comes to snipping. I'm kind of running out of time. Um, you know, nipping the slide and then pasting. So can you break down how many subchapters are here? Let's see if it can do it. Like yeah, it still makes a lot of mistakes. So no, we did that. We did that. So like I said, it's not able to understand. If I go all the way back, see, I never copied that. Copy, paste. So you shouldn't see subchapter 1. It still represents it. It still says it. Because again, it's not able to understand, right? So it actually starts from number 5. All right. So because you were not able to read, it actually starts from number 5, not number 1. All right. Try to understand what is going on. Um, you will waste a lot of time. All right. So explain number 5. Go. Explain number 5. How many are there? You have to remember because it'll forget. So explain number 5. Go. I want to understand. I'm very new to this. So Boolean algebra means logic using bit. So instead of using 2, 5, 10, whatever, you only use 0 or 1. So you can have 0 which is false, 1 which is true, or you can have 0 which is off, 1 which is on. And so the four main operators are AND, OR, XOR, and NOT. Those are the foundation. So Boolean algebra. Boolean algebra. So logic uses bits. So what is Boolean algebra? So what is Boolean algebra? This means that logic uses bits. So if I have AND gate, OR gate, NOT gate, XOR gate. So obviously you know the truth table for AND, right? AND will be 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1. OR gate will be 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1. Okay, let's do an example, a real life example. So let's say, let's say port 443 is open and TLS certificate exists. So cybersecurity example. Cybersecurity example. For example, if you have port 443 open and you have TLS certificate existing, then you're going to say that HTTPS would be port 443 that is open and TLS because you need both of them. So HTTPS requires both. There's another one which is bitwise example. If you have 1010 and you have to have 1100, so 1 and 1, 0 and 1, 1 and 0, 0 and 0, so there is 1 0 0 0, so 1000. So it's used in subnet mask, it's used in permissions, it's used in extracting the bits, it's used in packet parsing, it's used in flags, it's used in malware analysis. So where is it used? So where is it used? So subnet mask and permissions, extracting bit, mask analysis or malware analysis, then you have flags, whatever. Or operation is pretty easy. So either or can be true, right? So or operation, so or can be, let's say host is existing if scanner A exists or scanner B exists, or if any of the scanner detect it. So meaning if any of the scanner detect. You got a XOR NOT gate which removes or inverts the permissions, and you have XOR gate which toggles the permission. So main perspective is that AND gate So AND gate checks for performance, OR gate adds the performance, OR gate adds the performance, NOT gate it either reverses or inverts the permission, not performance, permission. NOT gate either reverts or inverts the permission, and XOR gate toggles permission. Right? Cool. All right. Um, let's move to how many are there? So there is 16 of those. All right, let's do 6 and 7 as one. Let's do let's do that. Mhm. Oh shit. It's gonna rain now. It is gonna rain, 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 and rain. Will it rain tomorrow also? No, it's not going to rain tomorrow, but it's going to be very windy tomorrow. Thursday it's going to be hot. Friday it's going to rain. Saturday it's going to rain. What about Sunday? It's going to be hot. বলেন আসেন আহ, বসে আছি বলেন I'll see. Sure. I'll see about it. Don't worry about it. হ্যাঁ sure. আহ, আচ্ছা আগে এটা শেষ করি তারপর আগে এগুলো একটু শেষ করি তারপর Sure. Afternoon. Sure. আর আমার চ্যাট জিপিটি মডেল পাসওয়ার্ডটা নিয়ে ফেলেন আপনি নিজে করে ফেলেন হ্যাঁ আমি আপনাকে পাসওয়ার্ডটা দিয়ে দিব পাসওয়ার্ড আর ইমেল দিয়ে দিব 100%. Mm, So using bets plus logical versus bitwise operation. So these two sections are deeply connected. The bits can represent collections of state, and then C has two different kinds of logic. So bits can represent collections of states. C has two different kinds of. Okay, I don't understand. Suppose the number of bits is 0, 1, 2, 3, whatever, and each bit position represents whether something exists in a set. So for example, suppose that you have 0, 1, 1, 0, 1, 1, and bit position 3 is 1, bit position 2 is 0, bit position 1 is 1, bit position 0 is 1. Then element 3 exists, element 1 exists, element 0 exists. So you 0, 1, and 3. So 1 means exists, 0 means absent. Okay, it made it confusing again, but I'll try to understand what's going on. So bits can represent collections of states. So can bit can represent collections of states. So C will have two different kinds of logic. He has two different kind of logic. The professor says, suppose we number the bits like 0, 1, 2, 3, whatever. And each bit position represents whether something exists in a set. So if my binary is, let's say, 1, 0, 1, 1, and each position, so 1, 0, 1, 1, and each element position will determine whether the bit position exists. Bit position exists. If I have 1, 0, 0, 1, 2, 3, then I can say that no, it's the other way around. 0, 1, 2, 3, then 0 exists, 1 exists, 2 doesn't, and 3 does. Therefore, I'll have 0, 1, 3. So let's say, for example, if I have bit and if I have service, I have 0 as HTTP, 1 as HTTPS, 2 as SSH, and 3 is FTP, and my binary is 1011. Then I'm going to say 0, 1, 2, 3. Then 0 is, so HTTP exists, HTTP exists, HTTPS exists, FTP exists. Oh no, then you have to do intersections. Okay. Um, okay, why do you have to? So after figuring out whether the bit position exists, then you have to do the truth table. But why? Now suppose set A is 1011 and set B is 1101. Now you want to intersect or find the union and find the difference. But how do you know when to use and or not XOR? It makes sense. So if I get this binary, then I'm gonna, so let's say for example, so okay, I understood. So what happens is that, so let's say if I have bit position and I have the service, let's say I'm gonna have HTTP, HTTPS, SSH, and FPS. I'm gonna say these all are 0, 1, 2, 3. If I have 1011, 1011,